Hello everyone, Namaskar, welcome to Maths Guidance and welcome to the fourth lecture of chapter number 10, that is circles. So in this lecture we are going to study the angle subtended by an arc of a circle. Alright, we have already discussed the angle subtended by the chord of a circle, so we will see that how it differs from the chord when we discuss about the arc of a circle. Alright, and one important theorem, very important theorem, we are going to study here in the fourth lecture, that is angle subtended by an arc at the center is double the angle subtended at any other point of the circle. Alright, and two more theorems we are going to discuss in this lecture, and the concept of cyclic quadrilaterals we are going to touch a little bit of the concept of cyclic quadrilaterals. Alright, then from the next lecture we will discuss about cyclic quadrilaterals, properties of cyclic quadrilaterals. Alright, so let's start the chapter lecture number 4, and I hope you are liking the videos. Please watch until the end. Thank you for giving the time. So friends, let's start the topic angle subtended by an arc of a circle. Alright, so first let's understand, let us suppose this is a circle and we are having two chords of equal length. Let us suppose this is one of the chords, this is second chord. Let us suppose this is A, B, and this is C and D. So AB and CD are equal chords. Alright, AB and CD are equal chords. Okay, so what is the relation between the arcs AB and CD? This is the arc AB and this is the arc CD. So we will see that what is the relation between these two arcs. Okay, so if you cut this arc AB, cut this arc and you put it here on CD, you will observe that they both are superimposing each other. So basically they are congruent. Okay, so if AB and CD are equal chords, then the arcs AB and CD are also congruent. Arcs AB and CD are also congruent. This you can verify by doing this simple test. Okay, arcs AB and CD are also congruent or are congruent. You can write AB and CD are congruent as they superimpose each other. As they superimpose each other, impose each other completely. Okay, each other completely. You can verify this by taking another chords, another circle. Alright, each time the same result will occur completely. So basically we can write this sentence as follows: if two chords of a circle are equal, then their corresponding arcs are congruent. Its converse is also true. That means what? Its converse is also true. That means if the arcs are congruent, then you can say that the chords are equal. Alright, converse, if the arcs are congruent, if the arcs or two arcs are congruent, then their corresponding chords are equal. Alright, so we have understood this thing, that if the two chords of a circle are equal, then their corresponding arcs are congruent and its converse is also true. Now we will understand the angle subtended by this arc. Alright, like this, subtended by the arc at the center. Let us suppose this is one arc AB. So this one, angle subtended by the arc at the center. Since arcs are having two parts, one is minor arc and one is major arc. Okay, major arc. So in terms of arcs, how we define the this angle, let us understand. All right, so let's move forward. Now let's understand the angle subtended by an arc at the center. All right, so let us suppose this is a circle. This is a circle and this one is an arc AB. All right, this one is an arc AB of the circle. So the angle subtended by this arc at the center means basically the minor arc is subtending this angle AOB, and the major arc is subtending this angle like this. All right, and we call this angle as reflex of this angle. You have studied in earlier chapter. All right, so this is angle AOB and this one is reflex angle AOB. So we define the angle subtended by an arc at the center as, let us write it, it is defined as the angle subtended by the corresponding, it is defined as the angle subtended by the corresponding chord at the center in the sense that minor arc is subtending this angle. Minor arc is subtending angle AOB and major arc is subtending reflex angle AOB, reflex angle AOB. So this is what we mean by angle subtended by an arc at the center. It is similar to the angle subtended by the chord. The only difference is this is the angle subtended by the minor arc, and this one is the angle subtended by the major arc. All right, now we can write one more property like this, that congruent arcs, if the arcs are congruent, then they subtend equal angles at the center. Likewise in the case of chords. So this is the property of an arc subtended of an arc property. Okay, that congruent arcs or equal arcs subtend equal angles at the center. Likewise in the case of chords. Okay, we have studied this. If there are two equal chords, then the angles subtended by the chords at the center are also equal. We have seen its proof also. So with the help of this theorem and this definition, we can say that congruent arcs or equal arcs subtend equal angles at the center. All right, so angle subtended by the chord of a circle is equal to the angle subtended by the corresponding arc at the center, like minor arc, let us suppose. Okay, now it gives rise to another theorem, and we will study that theorem. That is very important theorem. Okay, so let's go to that theorem. Now let's understand this theorem. It is the most important theorem of this chapter. Let's understand it and let's see its proof also. All right, so the theorem is like this: the angle subtended by an arc at the center is double the angle subtended by it at any point on the remaining part of the circle. All right, we will see its proof. And we will consider three cases. Okay, so first of all, let us see case 1. Okay, let us see case 1. Case 1 is when arc PQ is minor arc. When arc PQ is minor arc. All right, that means if this is the figure, this is the circle, this is the arc PQ, this is the center O. First it will come like this, the figure, and at any other point, let us suppose the other point is this one is O, this one is A. Okay, so when arc PQ is minor arc, then we have to prove angle POQ is equal to twice angle PAQ. This is what the theorem says. The angle subtended by an arc at the center, this angle is double the angle subtended by it at any point on the remaining part of the circle. Let us suppose this is the other point A. Okay, so we have to prove this one. Let us write the given thing. Given is arc PQ subtends angle POQ at the center, and angle PAQ at any other point. This is a given thing. So case 1 is this. Now let us understand the case 2. Case 2 is a case when this arc PQ is actually the diameter of the circle. Alright, so this will be point this will be point O, and any other point, let us suppose this is point A. Okay, so this angle and this angle. So case 2 is what? Case 2 is when arc PQ is semicircle arc. Okay, now what is case 3? Case 3 is this figure. Suppose this is the arc PQ, the major arc, this one, major arc. Okay, so this angle, it will this major arc will subtend at the center, and let us suppose this is the point, any other point. So case 3 is when arc PQ is major arc, when arc PQ is the major arc, Alright, so let's see the proof in all the 3 cases. Now what we are going to do, it will apply to first 2 cases, and then we will see what the condition in case 3. So proof is like this. Let us do one construction. Okay, this is arc PQ, this is the center, and this is any other point PAQ, this is O. Let us join this one like this. Let us take this point B. Let us join. Construction is join AO and produce it to B. Produce it to point B. Alright. Now this is making an angle here, angle BOQ. If this is the triangle AOQ, so we will write like this: in triangle AOQ, angle BOQ is the exterior angle. Angle BOQ is the exterior angle, and we have learnt that this exterior angle BOQ is equal to sum of 2 interior opposite angles. Alright, that is equal to angle OAQ plus angle OQA plus angle OQA. We know this theorem. I hope you remember this one, that exterior angle is equal to the sum of 2 interior opposite angles. Okay, let us suppose this is equation 1. Now this is equation angle BOQ equal to OAQ plus alright. Now this angle, you see that this is the radius of the circle. This OA and OQ are actually the radii of the circle. Okay, That means what? That means this angle is equal to this angle basically. So we can write it as angle BOQ is equal to twice angle this one OAQ. Okay, this is equation 2. Similarly we can write angle BOP is equal to this angle plus this angle. Means that if I am writing directly, then we can write that angle BOP is equal to twice angle this one is equal to twice angle OAP, and let us consider this as equation 3. Now adding equations 2 and 3, we get what? We get angle BOQ plus angle BOP, that is equal to twice angle OAQ plus angle OAP. This implies angle POQ basically. POQ is equal to twice angle PAQ. Hence proved. Okay, this is what we have to prove. Angle POQ is equal to twice angle PAQ. The angle at the center is double the angle at any other point of the circle. So this proves our case 1 and case 2, this case and this case. But for this case, the angle POQ is equal to twice angle PAQ, but that angle POQ is a reflex angle. Alright, reflex angle POQ is equal to twice angle PAQ in case 3. Okay, so this was very important theorem, and you have to study it carefully, because in many questions you will have to use this theorem. Let's see it once more. The angle subtended by an arc at the center is double the angle subtended by it at any other point on the remaining part of the circle. Alright, so this is the angle subtended at the center POQ, and this is any other point A, angle PAQ. So basically angle POQ is equal to twice angle PAQ. Alright, we have to prove this one. This is the theorem actually. Angle POQ is equal to twice angle PAQ, and 3 cases arise. First case is when arc PQ is a minor arc, so this figure. Second case, when arc PQ is a semicircle arc, this one. Third case, when this arc PQ is a major arc. Alright, so in all the 3 cases we will prove like this. We will join this AO. In a minor arc we have seen it. Join this AO. Then we will use the property of the theorems from the chapter triangles. In this triangle we will apply this, that exterior angle is equal to sum of these two interior opposite angles. So, and also these two are radii of the circle, so basically these two angles are equal. So we will reach up to this, that angle POQ is equal to twice angle PAQ. When adding these two equations we get this one, and this proves the theorem. Okay, so I hope you have understood it very well. Now let's move on. Let's see some other theorems. Okay, now let's understand this theorem. It says the angles in the same segment of a circle are equal. Alright, let's see its proof. Angles in the same segment. Let's suppose this is the circle. This is the circle. This is the arc PQ. This is subtending an angle POQ at the center of the circle. Let us suppose this is any point PAQ, and let us suppose this is any other point. So it is subtending the angle PCQ. Alright, this is the angle at the center. These are 2 points. So from the theorem we have studied, we can say that angle POQ is equal to twice angle PAQ. We can say this, twice angle PAQ, because of the theorem that angle subtended at the center is equal to twice angle subtended at another point. Also we can say that angle POQ is equal to twice angle PCQ, because this is also other point of the circle. So we can say this. Now from this 1 and 2, from equations 1 and 2, if we compare, we get twice angle PAQ is equal to twice angle PCQ, because these are equal. This implies angle PAQ is equal to angle PCQ. This is proved. Angles in the same segment of a circle are equal. Okay, this is the same segment and it is equal. These two angles are equal. So this is also one of the important theorems. Angle PAQ equal to angle PCQ. Now one more property we can derive, that angle in a semicircle is a right angle. Let us write it and we will prove it also. Angle in a semicircle. Angle in a semicircle is a right angle. Right angle. We can see its proof also. Let us suppose this is a circle. This is the diameter of the circle. Let us suppose this is PQ. This is center O. Okay. Now this POQ is actually 180 degree. Angle POQ is equal to 180 degree. Okay. And this is equal to is a right angle. Okay. This is any other point at the of the circle. This is another point of the circle. Now we can say that angle POQ is equal to twice angle PAQ from the very theorem we have studied just before. This implies angle PAQ is equal to angle POQ divided by 2. That is equal to 180 degree by 2, because this is linear pair. That is equal to 90 degree. Hence angle in a semicircle is a right angle. Angle in a semicircle is a right angle. All right. So if you draw any other points, angles at any other points, this is always 90 degree. Like here also you can do. Okay. So this is always 90 degree. So this is also an important property. Okay. This one and this one, all of these are important. Angles in the same segment of a circle are equal. Angle in a semicircle is a right angle. Now let's move forward. Now let's understand the last theorem of today's lecture. The theorem goes like this: if a line segment joining two points subtends equal angles at the two other points lying on the same side of the line containing the line segment, then the 4 points lie on a circle, that is, they are concyclic. This is basically the converse of the theorem that we have studied, that this one. Angles in the same segment of a circle are equal. This one is converse of this theorem. Angles in the same segment of a circle are equal, and this is the converse. Alright, so we will see how we see the proof of this theorem. Okay, now let us first of all draw the figure. This is the line segment. Let us suppose AB. As per the theorem, it is given that line segment joining 2 points subtends equal angles at 2 other points. Okay, this is the line segment AB, and let us suppose this is point C, this is point D. Okay, so it subtends equal angles like this. This is ACB, this is ADB. Okay, so basically we have been given that this given is angle ACB is equal to angle ADB. This is point D, angle ADB. Alright, and we have to prove that these 4 points lie on a circle. We have to prove, let us write it, to prove that points ABC and D lie on a circle, or they are concyclic. They are concyclic. Alright, we will see its proof. It's a very good proof. So let's draw a circle passing through these 3 points A, B and C. We know the way to draw the circle. Let's draw its perpendicular first of all, and its perpendicular also. It will join at a point, and then you draw the circle like this. You will draw the circle like this. Suppose this circle is not containing this point D. Alright, suppose. So it will cut somewhere here. let us suppose this is point E, or it will cut somewhere in the extended part E dash. Okay, somewhere it will intersect. If not here, then there. Now let's join it. Join the angles. This one will be the angle and this one will be the angle here. So AEB and AE dash B. Now if this point lie on the circle, suppose point E lie on the circle, point E lies on the circle, let us suppose lies on this circle, then what we can write? Angle ACB is equal to angle AEB. Okay, we can write like this, but we have been given that angle ACB is equal to angle ADB. This is given. Alright, and this from the theorem we can write that angles in the same segment are equal. We can write if this lies on the circle. But if you see, this case is only possible when this E coincides with D. When this E coincides with D, then and only then this is possible that these two angles are equal. Otherwise, this angle ACB equal to angle AEB and angle ACB equal to angle ADB, it cannot happen like this. So points E and D must coincide. Okay, and similarly we can write off this E dash, that angle ACB equal to ADB and angle ACB equal to angle AE dash B. So this D and E dash should coincide. Okay, so this is the proof of this theorem. And from here we can say that this A, B, C and D lies on the circle. Okay, hence we can derive that A, B, C and D, all these points lie on a circle. This is the proof of this theorem. This is the converse of that theorem, that angles in the same segment are equal. The theorem goes like this: if a line segment joining 2 points, these 2 points, subtends equal angles at 2 other points lying on the same side of the line containing the line segment, means this point C and D. The 4 points lie on a circle, that is they are concyclic. Okay, so given is angle ACB equal to angle ADB. Alright, angle ACB equal to angle ADB. So we have to prove that these 4 points lie on the circle, and we will consider that the point E lies on the circle and not point D. Alright, so angle ACB equal to angle AEB, but we have been given that angle ACB equal to angle ADB, and this will happen only in only case when these points E and D coincide. Similar is the case with E dash also. So basically these 4 points lie on a circle. Alright, okay, now let's move on. So friends, in this lecture we have seen 4 theorems basically, and we have seen its proof also. The first one was the angle subtended by any arc at the center is actually double the angle subtended by it at any other point of the circle. Second one, we have seen its proof also. Second one, we have seen that angles in the same segment of a circle are equal. And third one, from this we have derived that angle in a semicircle is a right angle. And the fourth theorem we have seen, it was the converse of that theorem, that angles in a same segment are equal. Its converse is like this, that if 2 points subtends equal angles at 2 other points lying on the same part of the segment, then the 4 points are concyclic. We have seen its proof also. So I hope everything is clear to you, and we are left with only one topic, that is cyclic quadrilaterals, and we will see it in the next lecture. And then of course our favorite question and answer session, we will do it. So let's wrap up this lecture number 4 here, and hopefully in 2 more lectures we will be able to complete this chapter number 10. Alright, so thank you for joining me, thanks for giving the time, thank you very much.